Okay, so welcome everybody this week's quantum computing, quantum information seminar. We have a pleasure to host Oskar Leimkuhler from UC Berkeley. Oskar is gonna tell us about exciting subject of potential exponential speedups in quantum chemistry. The screen is yours. Thanks for joining us all the way from the US.
Great. Thank you everyone for coming, and thank you very much to the hosts of this meeting. It's great to be here. Yeah, okay. So I figured that some people in the audience might be less familiar with the subject domain of quantum chemistry. So I thought that I would start there and sort of focus on those aspects of the work. So I'm interested in ab initio methods, which are methods to try and understand and model chemical phenomena from first principles. In particular, the electronic structure of molecular systems, so ground and low-lying excited states. And it may be a bit of an exaggeration to say that the ground and low-lying excited states gives you all of quantum chemistry, but it's not too much of an exaggeration. You can compute from this absorption spectra, material properties, drug reactivities, and many other useful properties of interest. And within the application domain of quantum chemistry, we have this notion of chemical accuracy, which means that really just means that we want to match the precision of the best possible experiments. So this roughly translates to resolving energy levels to within about 1.6 millihartz. And this figure right here is just from I just like this, these real images of I think these are the 1s orbitals of hydrogen. I just find it amazing that someone was actually able to image these things. And it's nice when you're working, I think, in a very abstract, on a very abstract topic, to remind yourself that these things are actually real. So we can even see these things. So this is a one electron wave function. The difficulty arises when
simple question, like layman question. So how those images are made?
I do not know. It's some experimental technique that I couldn't follow, but I'm very impressed that someone was able to do it. Yeah, so I'm really a theorist, as I think will be very clear throughout the talk. But yeah, I just think it's nice to remind oneself that all of the things we're going to be talking about in the rest of the talk are actually real. You need to take the quantum nature of molecular systems seriously, because we can even see it in experiment. So for a single electron system, like a hydrogen atom, obviously we can solve this analytically. This is standard stuff in introductory quantum mechanics courses. The difficulty arises when we have multiple electrons. Then this becomes a very, very difficult problem to solve. And the development over the last century or so of quantum chemistry has been really focusing on heuristic methods. So finding good approximations to the many-body wave function of a quantum chemical system. And a clever heuristic can significantly reduce the cost of practical calculations. And the perspective that I'm going to take in this talk is that heuristics can also serve as a guide for more rigorous analysis. So there is this role played of chemical intuition, which is a bit like saying sometimes we can guess that something will work before we know why, or before we can prove that it will work. Because these heuristic methods are built up over many, many decades of trial and error, and we have good reasons to think that something might work before we can actually come back around and prove that this should give us some level of accuracy, for instance. There are also sort of loose descriptors that quantum chemists use to describe different kinds of features of correlated wave functions. So broadly speaking, the dynamic correlation, not to be confused with dynamical evolution of the wave function, really just is describing the perturbative features of the wave function. So by that I mean if you have some wave function that is close to a mean field solution, and then the electron correlations only add perturbative corrections to that. So it's sort of qualitatively a mean field wave function with some slight corrections. This is what we refer to as dynamic correlation. Static correlation refers to the non-perturbative features of the wave function. So if it's not even qualitatively close to a mean field solution, then we would say that it is statically correlated. These are also called weak and strong correlation, but I'm going to use dynamic and the words dynamic and static to draw a distinction between that and weak and strong simulation of quantum circuits. It is unfortunate that there's an overlap there, but that's just the choice that I'm going to make.
Sorry, because I'm not that familiar with quantum chemistry terminology. So like dynamic doesn't have to do with dynamics of molecules, but more with methods with which we like level of accuracy of confidence we have to those methods. So to
right, I will say more on this later. So it might become a bit more clear what I mean by these terms in the context of second quantization. Yeah, but it's not really referring to dynamical evolution. It is a property of the stationary states of the Hamiltonian. So it's worth asking how quantum is quantum chemistry. So by this I mean, in some sense, we know that quantum chemistry is a natural problem for a quantum computer, in the sense that if we had access to a fault-tolerant quantum computer with unlimited depth of operations and a large number of qubits, we know how to map quantum chemical systems onto a quantum register. And the algorithm of choice in this regime is quantum phase estimation, which, given an input state that has reasonably high overlap with, say, we're trying to resolve the ground state, given that we can prepare an input state with reasonable overlap with the ground state, then the refinement cost for the energy estimate is polynomial in the system size and the inverse precision. So this paper, which these figures are from, Lee and co-workers from 2023, they pointed out that it's not a priori clear whether there is a verifiable quantum advantage for quantum chemistry just off of this argument, because they point out that in the regime of molecular systems that are dynamically correlated, meaning they're qualitatively close to a mean field solution, we know that there exist classical heuristics that can match the poly n 1/epsilon refinement cost. The sort of target regime for quantum computing would be the statically correlated regime. But in this case, it can be non-trivial to even find a starting state that has high overlap with the ground state. So it can be non-trivial to prepare such states. I should say that in that paper, they really considered classical heuristics to prepare these initial states for phase estimation. The perspective that we're going to take in this talk is that it may be more feasible to prepare high overlap ground states using quantum heuristics. So we are not really going to talk about phase estimation in the fault-tolerant regime, which is very costly in terms of quantum operations. Instead, we're going to focus on quantum heuristics for near-term devices. So there's a kind of gap in the literature in near-term quantum computing. There has been much work on finding low-depth quantum circuit families for which there are provable quantum speedups, typically in the sampling complexity. So quantum supremacy is kind of a word that people throw around to mean, can we perform a provably classically intractable task with depth-limited quantum computers with a limited number of qubits, and maybe some degree of noise, which is what I mean by today's or tomorrow's quantum computers. On the other hand, practical quantum advantage is really asking, can we do something useful with today's or tomorrow's quantum computers? So find a speed up for a useful task such as quantum chemistry. And in the context of quantum chemistry, the sort of prototypical near-term method that people talk about is VQE, the variational quantum eigensolver, and more recently subspace methods. So more on this second point later. Oh, whoops. So our question for this talk is, can we combine both of these? Can we find a useful quantum heuristic that has a provable speed up over any classical heuristic in the application of quantum chemistry? So just a brief note about the scope and assumptions of the talk. So we're going to treat molecular systems within the non-relativistic quantum theory. So we have a system of point-like particles characterized by mass, charge, and spin, positively charged nuclei, and negatively charged electrons. And we're also going to treat our systems within the Born-Oppenheimer approximation, which is just saying that the nuclei are much heavier than the electrons. The electrons move much faster than the nuclei. So in practice, we can decouple the degrees of the nuclear and electronic degrees of freedom and treat the nuclei as fixed classical particles and the electrons as identical spin 1/2 fermions that will exist in some kind of quantum probability distribution in the nuclear potential. So I should say this is not always a good approximation, but in many cases it can allow calculations with very high accuracy. So it is often a very good approximation. By far the biggest assumption on this slide is the last one, that we're going to assume that the quantum hardware is good enough, the gates are of high enough fidelity to run small circuits with virtually no noise. So we're not going to take into account noise effects within this talk, but of course they are very important if you actually want to run an experiment on real quantum hardware to show an advantage. But that'll be beyond the scope of this talk. Any questions so far, or is everyone all right with this? Okay. So I'll go quickly through the next few slides. For people who have seen this before, it'll be a review. If you haven't seen this before, or if you saw it a long time ago, then it will be a refresher. So this is the just going through the basic framework of electronic structure and second quantization. So we start by taking a discrete set of basis functions. So any space filling, I mean, for our purposes, it doesn't matter too much what these are. Obviously, for practical calculations, it matters a lot. Typical choices are atom-centered Gaussians or plane waves. But this can just be any set of space-filling primitive functions. We take linear combinations of these to construct a basis set of molecular orbitals, which are single particle wave functions with some distribution in space. and they form an orthonormal set. So a key sort of, I guess the sort of focus of this talk in some ways is going to be these operations called orbital rotations, which are just unitary transformations of the orthonormal molecular orbital basis. So we're redefining each molecular orbital as a linear combination of the previous set. And I should say here that if anyone has questions at any point, please don't hesitate to jump in and interrupt. If any of this is not clear or you just want to clarify anything.
Sure. Like I think we are good. We have at the moment some okay, depends. Like some people are really like experts on that. Like I think Zoltan has joined us, for example, or like Emil from company that actually like does like uses you know, quantum, like works on algorithms for quantum chemistry. So yeah. So we're gonna interrupt if you know we have.
Okay. So yeah, I am assuming that there may be some people who are less familiar with this, so I'm just gonna go through it briefly. So now we have a basis of single particle functions. We combine these to form a basis of many electron wave functions, which are spanned by Slater determinants, which is just an anti-symmetrized product state. So this is we are treating the electrons as spin 1/2 fermions, which means that when we interchange the coordinates of any pair of particles, the wave function has to take on a minus sign. This is really the key feature of fermionic systems. And a Slater determinant is just a very simple way to construct an anti-symmetrized wave function such that the interchange of any pair of coordinates gives you a -1 sign. So we map a set of Slater determinants to occupation number vectors which span the Fock space. So we have zeros and ones for either an unoccupied or an occupied orbital. And so this gives us a set of bit string states which span the Fock space. Within this framework, we map Fock space operators to products of creation and annihilation operators in linear combination, which satisfy also these fermionic anti-commutation relations. Yeah, so this is just the sort of standard framework of second quantization. So for example, the electronic structure Hamiltonian is a sum of 1 and 2 body excitation terms, where the 1 body integrals encode the kinetic energy of the electrons as well as the electron nuclear forces, attractive forces. And the two body terms encode the electron-electron repulsive Coulomb interactions. So these coefficients, they encode all of the chemical physics of the problem, and from then on we can treat everything just as you know, matrix vector operations in an exponentially large state space. So if we simply diagonalize in the space of all of the Slater determinants that span this space, this is referred to as full configuration interaction, or FCI for short. And within the bounds of the approximations that we've made, so the non-relativistic quantum theory, the Born-Oppenheimer approximation, and the finite basis set, this corresponds for our purposes to the true ground state energy of the system. The issue with just diagonalizing in this space, of course, is that the dimension of the Fock space grows exponentially with the number of particles, i.e. the system size. And this is true also for the fixed particle number block, where everything that we care about is going to take place. This constraint of fixed particle number is necessary to accurately describe a closed molecular system. And okay, so to come back to orbital rotations. So an orbital rotation operator, as I mentioned, is a unitary transformation of the molecular orbitals. So it is characterized by an n by n coefficient matrix, where n is the number of molecular orbitals. And it can also be expressed, of course, as a Fock space operator. So that would be represented as a in principle by a 2 to the n by 2 to the n unitary matrix. And the Foulis theorem gives an explicit expression for this in terms of fermion operators. So basically, what this is saying is that you can reason that if you start with a Slater determinant that is a state of uncorrelated electrons, and then you rotate the orbitals, you will have a Slater determinant in rotated orbitals, which is also a state of uncorrelated electrons. It is also true that if you evolve that starting state under a one-body Hamiltonian, meaning that there are no two electron interactions or two or higher body interaction terms, then oh, is there some mark on the slide there?
Right. So please, like, okay, somebody, we probably have yeah, like open, like keep like whiteboard for some reason. Arturo, can you like maybe try to undo it? I don't know, or I don't know who has joined, like the right. Yeah, that. Okay, the
That's
guy.
fine. I'm gonna try and
Apologize
ignore
for this.
it.
I maybe Arturo, can you like just like cut like maybe in the settings one you can do it because now it's okay.
Yeah, got it.
Who did that?
Somebody who came and logged out. Anyway.
No, I removed it.
Okay, cool.
Okay.
All right.
Sorry, Oskar. Please go.
No,
Right.
Yeah, so I was just saying that so there you can reason that there has to be a correspondence between one body evolution under a non-interacting Hamiltonian essentially, and orbital rotations. So they are one and the same thing. And in the second quantized formalism, this manifests for a discrete basis set in the second quantized formalism. This manifests in the Foulis theorem, which can be stated like this. So if X is a Slater determinant, G acting on X is a Slater determinant in rotated orbitals. And it is also known that the overlap between Slater determinants in rotated orbitals is efficiently computable in polynomial time on a classical computer. The Hamiltonian can be expressed. So we saw on the previous slide, the electronic structure Hamiltonian can be expressed in order n to the 4 strings of fermionic operators. And this is true. It can be expressed in any orbital basis. It will just be a transformation of the Hamiltonian coefficients. So the key point here is that the choice of orbital basis can significantly affect the computational hardness of solving the second quantized electronic structure problem. If you solve with a clever choice of basis, you can often reduce the cost to something that is efficient on classical hardware. But if you try and solve the problem in the wrong basis, in the wrong orbital basis, it can quickly become very, very intractable. So typical choices of single particle basis are mean field orbitals, selected by a Hartree-Fock procedure, or spatially localized orbitals. But the point that we're going to try and make in this talk is that the chemical systems that we're interested in are those for which there is no one orbital basis that leads to an efficient solution.
So can I ask, Oskar, just to be certain? So you say that, okay, because like everything sort of depends on the choice. Like given a physical system, everything is going to depend on the choice of the basis of orbitals that we pick, and like from the physics perspective, we just like limit ourselves to subset of the relevant Hilbert space. So like. So you say that there are some like chemical molecules for which some choice of orbitals gives like actually a single stated determinant for some choice of orbitals is good.
Yeah. So for example, if you have a one-dimensional system, then using a set of molecular orbitals that are localized in that space, you can think of it as you would have like a sort of chain of orbitals in space, and the interactions between far separated orbitals on that chain would be very small because they decay according to the Coulomb force. But ones that are closer together would be large. So if you try and solve in that localized basis, it can make the problem much easier because you have these very localized correlations. But if you rotated the orbitals, so you sort of mixed them all up so that all the orbitals were delocalized over the chain, it might make the problem much harder, right? That's kind of the point that I'm trying to make here.
Okay.
Can I make just a comment here?
Yeah.
It's possible that, so there are exactly now, Oskar actually said that there are two things here. One is the choice of the one particle state, that is some orbitals that you choose from the full space, okay? And then the next thing is that if you have that one particle state, which are the basis orbitals that you use? Because if you rotate it, well, maybe a DMR, I mean, maybe it's not a single Slater determinant, but maybe a DMRG procedure would be good. If you put it into in a different basis, then it might not be good. But it's the same Hamiltonian, just written in different basis.
Yes. Yeah. Yeah, so this is just a unitary transformation of the Hamiltonian. So it sort of describes a kind of set of related Hamiltonians which are isospectral, right? So it's the same physical information, just in a different choice of basis functions, right?
So, hi, I've got a question, Emil. So what is your opinion on using plane waves as in quite distant Ryan Babush paper on solving the electronic structure problem with delocalized plane waves from the beginning? Do you have any opinion in favor or against these localized against the localized basis? Because
yeah, no, I think that plane waves can be very useful. I think that it comes down to what kind of system that you're trying to solve. For instance, in periodic systems, often plane waves are the orbitals of choice because they map very naturally onto that periodic structure of the system. But also for so they're very commonly used in fault tolerant settings, because with quantum algorithms such as phase estimation, they can lead to so if you work in a first quantized representation, then plane waves can be a very efficient orbital basis. So I think that is one of the contexts in which people think about plane waves a lot. So I'm sort of focusing on near-term methods in this talk, and in that setting, you can often get away with much more compact bases if you use localized Gaussian bases or something like this. But yeah, it really comes down to, there will be many factors which will influence which kind of basis that you would want to, or which kind of primitive basis functions you want to use in practice. And I don't think there is sort of one right choice. It sort of comes down to what methods you are using and what systems you are looking at. But yeah, thank you for the question.
Okay, thanks a lot.
So I'm hopefully not too far behind on time. I'll try and speed up a little bit for the next few slides.
So we did not, sorry, like I think haven't, maybe I said like it's like we try to be like below 1 hour, including questions. I mean, we do have like questions in the like as now. So maybe like if we started like 10 minutes late, so if we could finish by 5:40 would be good, let's say. Yeah.
Great. Yeah, I will try my best to not get.
Yeah. I mean, but like we are relaxed as well. Like yeah.
Right. Yeah, so I'll maybe not spend a lot of time on the next couple slides, but this is just a brief tour of classical heuristics. So the notion of an ansatz is just a best guess wave function for the true ground state, some efficiently representable wave function. And ideally, we would like this to also be efficiently normalizable, which means that we can guarantee by the variational principle that the energy estimate we obtain is lower bounded by the true ground state energy. We also would like our method to be size consistent, which just means that if we have isolated molecular fragments, then adding an extra fragment to the system that doesn't interact with the previous should not reduce the accuracy of the method within either of those fragments. So it shouldn't add in any spurious correlations between the fragments. If they're well separated, then it should be it should really be a product state wave function. And the energy estimate should just be the sum of the energies within each non-interacting fragment. So the sort of one of the simplest classical approaches, we already saw that full configuration interaction is diagonalization within the space of all Slater determinants. Configuration interaction can also be performed within some subspace, some typically polynomially large subspace of Slater determinants. So for instance, if we chose all the doubly excited Slater determinants relative to some Hartree-Fock state, this can be good for moderate amounts of static correlation, but not so good for treating the dynamic correlation, which typically involves many higher lying Slater determinants, which would not be captured within this framework. Limited configuration interaction methods are typically variational, but size consistency is not guaranteed.
Sorry, can I ask? I got a bit confused about this static versus dynamic, because you mentioned that static sort of refers to, like, static properties refer to sort of ground truth, maybe given the like truncation of the single particle space. Let's say it's a ground truth, while dynamic refers to perturbative like effects. So let's say, so I don't like, what do you mean by static correlate, like static correlations and dynamic? So dynamic are corrections to some Slater determinant, and what are the static ones?
Yeah, so it's it is not kind of like a hard and fast distinction between the two. They're kind of loose terms which chemists use just to sort of qualitatively describe features of correlated wave functions. A good way to think about it is that if you have like one Slater determinant which sort of dominates in your wave function, and then everything else is just perturbative corrections, but you have sort of many higher lying Slater determinants which each contribute a small amount to the wave function, this would be a dynamically correlated wave function. If you have like a handful or some small set of Slater determinants which all contribute a lot to the wave function, this would be an example of static correlation, because you could not choose just one Slater determinant which is a good description of that wave function, right? So yeah, it's that's a reasonable way to think about it, I think. But yeah, like I say, they're not kind of like very precisely defined terms typically.
So, but is it like, should I think about it like, okay, like I have dynamical correlations if my wave function is sort of up to some corrections approximated well by a single Slater determinant,
right?
And I have static when it has, say, greater Slater rank, or like not rank, like more like it's a superposition, like non-trivial superposition of a bunch of Slater determinants, and I cannot reduce this number.
Yeah, I think that's the basic idea. Yeah.
Okay. Thanks.
So yeah, so to continue this point, couple cluster methods are another very common choice, and these are typically very good for treating the dynamic correlation, but not very good for static correlation. The idea here is that you have one Slater determinant which dominates your wave function, and then you introduce perturbative corrections to that through an exponential expansion of some generating operator which generates excitations. So here, for instance, we've used two body generators. So this would be a couple cluster doubles wave function. And this is usually very effective when the amplitudes are small. And then you can sort of these couple cluster type wave functions with some higher order corrections, I think CC-SDT, so singles, doubles, and some triples, is sort of regarded as the gold standard of quantum chemistry in the dynamically correlated regime. So these methods are all size consistent, but they're not variational, because if you truncate this expansion to some finite order, and also this is not a unitary operator here, this is not going to be necessarily normalized, this wave function. And actually normalizing these wave functions is one of the big challenges with these methods. So you can have energy estimates that go below the true ground state energy. Another classical method, which is I think somewhat interesting, is non-orthogonal configuration interaction, which is essentially a configuration interaction method where the basis determinants are expressed in rotated orbitals. So this again has the problem of recovering size consistency requires a number of Slater determinants that doesn't scale well. So this also suffers from the curse of dimensionality, but you can potentially gain some of the dynamical correlation through the orbital rotations. And finally, this is a somewhat different kind of approach. DMRG, which was already mentioned. The ansatz here is a matrix product state, which is a one-dimensional tensor network. And the parameters of the site tensors are obtained by the DMRG sweep algorithm, which is a very efficient form of variational optimization. The bond dimension quantifies both the accuracy of the wave function and the computational cost in terms of the memory requirement. So these kind of wave functions have loads of really nice features. They can capture both types of electronic correlations, but DMRG is typically considered to be better for treating the static correlation. They are variational and size consistent. And these types of wave functions can be exact for gapped one-dimensional systems, but they quickly become intractable for systems that do not have a one-dimensional area law of entanglement, requiring a bond dimension that scales exponentially in the number of sites. So they're really effective for one-dimensional systems, but less so for more general quantum chemical systems. So we know that the overlaps between Slater determinants are efficiently computable in polynomial time, but what happens when we go slightly beyond a single Slater determinant? Meaning, what if we have compact correlated wave functions in different orbital bases? So in this case, so this is the basis for what we're going to refer to in this talk as quantum multi-reference methods. They are a variant of quantum subspace methods, which some of you may have encountered. So the idea is to compute a set of Hamiltonian and overlap matrix coefficients between the reference states, and then so obtain those on a quantum computer, and then on a classical computer solve a generalized eigenvalue problem to resolve the low-lying spectrum. So two examples of this from previous work that we've done here at Berkeley. So the TNQE method uses reference states that are matrix product states of some fixed bond dimension in different orbital bases. The NOQE method uses unitary coupled cluster type states with amplitudes selected by classical methods, requiring no hybrid variational optimization. And in these previous works, we have shown how to apply standard Hadamard test type quantum circuits to efficiently compute these overlap and Hamiltonian matrix elements. So the question is, how hard is it to compute these matrix elements, for example, the overlap matrix elements Sij, on a classical computer? So this is saying, how hard is it to compute the overlap between some compactly represented correlated states expressed in different orbital bases?
Sorry, Oskar. So this Gij is just like product of two orbital rotations.
Yeah. So it would be like GI dagger GJ, I guess. Yeah.
Okay.
So it's just combining those into one orbital rotation, which transforms the basis. Yeah.
Thanks.
So this is going to be the focus of this is the question that we're interested in, and in the next few slides, I'll briefly cover the proof techniques that we used to understand this. They're sort of standard techniques, and as I'm sure you in the audience, I know that people from this group have done loads of work in this area, so I'm not going to spend a lot of time here. Yeah, so matchgate circuits are kind of the gate representation for orbital rotations. And in the case of matchgates, in the case of orbital rotations, we have to fix the particle number. So we restrict the form of these matchgates. These circuits have also been, of course, studied under the name of fermionic linear optics, in which case this would correspond to the passive case of fermionic linear optics. So examples are the fermionic swap gate, which is just like a normal swap gate, but introduces a minus sign when two electrons exchange their positions, similar to the construction of the Slater determinant, which we saw earlier, where if we exchange two particle coordinates, you get a minus sign. Something very similar is going on here. And fermionic swap networks are just nearest neighbor networks of these F swap gates, which can rearrange any ordering of the qubits on your register with the addition of these fermionic phase flips. Other examples include the Givens rotation gate and the single particle, the single qubit phase rotation gate. And in fact, these two gates are sufficient to construct any particle number conserving matchgate circuit. So for instance, you can express the F swap gate from the previous slide as some product of these. And so the connection to match gates was established. I guess the connection between particle number conserving matchgate circuits and orbital rotations. So evolution under a one-body Hamiltonian was previously established in this first paper here, and then later it was shown that any orbital rotation can be factorized into a linear depth sequence of these particle number conserving matchgates. So, but it is also the case that any matchgate circuit of any depth implements an orbital rotation, which means that any number conserving matchgate circuit must collapse down to this linear depth. And this also can be generalized to complex valued orbital rotations with additional phase gates. The expression here is just for real valued rotations, but complex values are not an issue. So just to situate this work in the context of previous work in this area, so this work is basically just extending a previous result from this Hebenstreit and co-workers paper of 2020 to the particle number conserving case. And there's been loads of work in this area previously. The question that we're interested in, or the sort of the connection that we're using, is that matchgate circuits with magic state inputs can be classically hard to simulate under simple complexity theoretic assumptions. And in particular, we extend this result of universality under post-selection, UUPS, to the case of conserved particle number. So we're going to prove this theorem.
Sorry, Oskar, just one comment, if I may, about the previous thing about this work. But I think it might be from the group of Barbara Kraus, right? So it's a very, I don't remember details of the work. It's a yeah, but I think it has to do about like just general complexity landscape of maybe like worst case matchgate plus magic states. So, but like I would maybe probably say that already, like there were some works by Bravi from early 2000s, both, I mean, probably Kitaev first and then some follow-up work on Bravi, from which one can basically infer, it's not stated like this, but you have some magic state injection, let's say, schemes there. So I think this statement probably can be, like this third statement can be inferred from their work already.
Right. Interesting. Yeah, I'm not sure I've seen that. You aren't talking about the fermionic quantum computation paper.
Yeah. I mean, so because isn't it sort of automatic that, roughly speaking, if some model is like universal, like after post-select, how is it, like universal after post-selection, you get this type of statements, right? Like,
So I think in this work, one thing that was different from Bravi's work, but it's not too much, so I'm signing with Meow, is that they showed that I think arbitrary pure so they showed a bigger set of resource states than the particular resource states that Bravi was using in some sense. But I would agree that Bravi has this this already.
All right. Yeah, I might have to go back and revisit that paper.
I mean, those are like hard papers to swallow, arguably, but like nice.
Yeah.
Sure. Yeah. So I mean, this is really just to say that this is the proof is really just an extension of previous results. The sort of I think the more important contribution of our work is to connect these complexity theoretic results to tangible applications in quantum chemistry. So that's what I'm going to show you after, quickly going through the this proof extension of ours. So we proved this theorem 1, which is just that the family of orbital rotation circuits with 4-qubit fermionic matchgate inputs is universal for quantum computation under post-selection. And from this follow the corollaries 1 and 2, which are about the classical hardness of strong simulation up to a multiplicative factor and weak simulation under the assumption that the polynomial hierarchy doesn't collapse. So the way that we do this is by it's much easier to prove that you can encode arbitrary logical computations under a dual rail encoding, where you just map the logical basis 0 and 1 basis states to particle number conserving states, the 0, 1 and 1, 0 states of a physical qubit pair. So I just have to plug in my laptop. Here we go. So a logical single qubit gate decomposes into Euler rotations, and these can be mapped to number conserving match gates, the phase and Givens rotation gates. The logical 2-qubit gate requires a gate that is not in the match gate set. So for our purposes, the CZ gate is just as good as the generic swap gate for this task. And we use this post-selection gadget to implement the CZ gate. So this doesn't deterministically implement the CZ gate. It implements it provided that we obtain a particular measurement outcome. But that is enough to prove universality under post-selection, which was what we set out to prove. So this completes the proof of theorem 1. And then we just apply standard complexity results to prove corollaries 1 and 2. It is worth noting that theorem 1 also implies that a hardness result for a more general family of quantum chemistry circuits consisting of single and double excitation gates, also in the conserved particle number regime. So this tells us that with polynomial overhead, we can encode any logical quantum computation into a generalized trosserized UCCSD circuit, meaning that computing the output probabilities up to a constant additive error is BQP-complete. So the interesting thing for us is how can we apply these complexity results to useful quantum chemical algorithms? Recall from one of the earlier slides that our quantum multi-reference methods use a wave function ansatz that is a linear combination of some small number of compact correlated reference states expressed in different orbital bases. So now we know from corollary 1 that exactly computing the overlaps between these correlated reference states for anything that can encode the fermionic magic states, which are just 4-qubit states, so slightly entangled reference states. This is gap P hard by corollary 1. And also additive error dequantization schemes that rely on being able to sample from somewhere in the middle of the circuit and then efficiently compute the partial overlaps. This is also ruled out by corollaries 1 and 2. So this means that, you know, that there is no obvious way to dequantize these things using classical algorithms for any correlated reference states that are even slightly more complicated than a single state determinant.
Sorry, can I have some specific questions just about
Sure.
Okay, so just in previous like in previous slides, you were talking about probability amplitudes, let's say, of passive circuits. Like we have passive circuit that acts on something, maybe it includes magic states, and then you're measuring particle number like in occupation basis, like or folk basis, right? So so strictly speaking, you need probably quite a lot of like magic states to okay, you like when you have statements like gap P and so on, like that refers to the fact that you have like family of circuits, like you're gonna need to have lots of magic there, right?
Sure.
To have such a okay, but okay, how do I proceed? So here you have those overlaps, Sij, Hij. Let's say focusing on Sij. So you have phi I, like those wave functions phi I and phi j. So should I think of them that I have that one of them is computational basis state and the other is tensor product of like some
So
determinant?
they might be a tensor product of magic states, for instance.
Both.
Yeah.
Okay, so then like okay, so this is like so then I have a okay, like I would expect computation of that is hard, but what you were talking previously actually has to do with not those overlaps, but the overlaps, like strictly speaking, function like when one of those functions is just computational basis thing, right?
Yeah, I see what you're saying. I guess I would not see why you know, if you have like tensor products of magic states on one side and a computational basis state on the other side, if that is gap P hard, I don't see why making the other thing also a tensor product of magic states would make the computation any easier.
Sure, I tend to agree. Like on the like sort of on the level of intuition, I tend to agree, but I don't, let's say, fully agree on the level of like fully rigorous proof. But it's not nothing. I'm not like I'm just
yeah. I see where you're coming from with that. I think so. If we think about like a sort of a practical algorithm to actually compute the overlap between these reference states.
Yeah.
So this sort of comes into the last point here on this slide. If you sort of slice the circuit anywhere down the middle, so you have like maybe it'll become clearer with a particular example. So if reference states are matrix product states, for instance, I mean, one thing you could say is that if you know you have a matrix product state on either side of this orbital rotation circuit, then either one of those matrix product states could be chosen to be the tensor product of magic states, or could be chosen to be a computational basis state, right? They have enough flexibility, representational flexibility, to represent either of those things. If you assume that these both sort of have a lot of magic in them, in that they both have some tensor products of magic states that they encode, then if you think about sort of slicing the circuit anywhere down the middle, from corollary 2, we know that weakly simulating, i.e. sampling from any of those partial circuits, will in general be classically intractable unless the polynomial hierarchy collapses. So it is unclear how you could dequantize this matrix element in practice using, I mean, it pretty much rules out any kind of sample-based dequantization scheme to compute this up to an additive error, right? And that's sort of, yeah, it's the argument that we make in our paper, that these kind of sample-based dequantization schemes are ruled out. So you would have to come up with something that no one has thought of before to find some way to dequantize these matrix elements. And yeah, I mean, I don't know, maybe you could train a large language model.
Sure. Just yeah, I'm not like okay, like I did, like, but like but just sort of just to make sure we're on the same page. So strictly speaking, like there is no, okay, like if those states phi I, phi j are, say, like are rich enough to encompass both Fock states or zeta determinants and tensor product of magic states,
yeah,
then in the worst case, I agree with you.
Yes.
Let's say about, like, okay, I just didn't, like, I think we haven't thought about just this type of overlaps, like when we had like our work. Like I think it should be still hard and right, although yeah. So I should say, because I think we got, like, from perspective of some people to the fairly interesting part, but at the same time we are like at the time limit.
Yeah, I realized
so
that.
What I suggest, maybe, if that's, I mean, me, I would be like quite interested to like maybe dig a bit more, but like maybe what about we give Oskar some time to finish the talk, maybe in 5 minutes, and then we continue with less formal discussion. Is
Sure.
it okay? Cool. So let's proceed like this. Yeah.
Yeah. All right. So I will try and wrap things up relatively quickly. Apologies for stretching the time limit a little bit.
No, it's also us asking questions. No worries.
Yeah. All right. So one example would be so matrix product states and rotated orbitals, and provided that we have enough representational flexibility in each reference state, then our corollaries 1 and 2 do apply. In principle, what we would like to show is that computing these things up to an additive error, closed simulation of these matrix elements up to an additive error, is ruled out unless there is some kind of polynomial hierarchy collapse. We can't, quite show that, but we can get quite close. But yeah, it would be in principle nice to be able to prove that actually the closed simulation up to an additive error is something that cannot be dequantized. So this is some stuff from a previous paper. We can map these kind of tensor networks for the off-diagonal matrix elements to Hadamard test quantum circuits and efficiently compute them up to an additive error with polynomially many shots, and the circuit depth for these kind of overlap or Hamiltonian matrix elements for a constant bond dimension, i.e. the bond dimension doesn't grow with the number of sites, then the circuit depth is linear in n, which can be much cheaper than unitary coupled cluster type methods, where this circuit depth is in general some superlinear polynomial in n. So in this previous work, I won't go through the details here, but we developed a natural extension of the classical DMRG optimization algorithm to the TNQE ansatz with an extension via quantum subspace diagonalization. So it's somewhat more costly in a number of measurements, but it can pay off in the reduced circuit depth. And in this previous work, we considered a sort of iterative orbital update scheme where during the tensor parameter optimization, we would also optimize the orbitals in a pairwise fashion. So this reduces the bond entanglement for each matrix product state and sort of offloads some of the information from that bond into the orbital rotations. So it sort of iteratively builds a set of orbital rotations that best represent each reference state. So quickly, some results from actual, well, toy systems, but one of them is a water molecule, which is at least a somewhat realistic molecule. So on the left here, panel A here corresponds to the dissociation of a water molecule. So this would be equivalent to running quantum circuits on 14 qubits. On panel B here, this would be equivalent to quantum circuits on 12 qubits, but it's a much more strongly correlated system. It's an octahedral arrangement of hydrogen atoms. So there can be a lot of static correlation in this type of system. So we compare against some classical analogs and show that the energy error can be reduced for the fully quantum version of this with orbital rotations between each reference state for an equivalent number of free tensor parameters in the ansatz. And we also compare this against a single reference BQE method with unitary coupled cluster with single and double excitations. This is also for the octahedral H6 system on the left panel here. And we can see that TNQE is both much more performant and much more cost effective. So on the right panel here, with increasing numbers of hydrogen atoms in the system, there is a dramatic reduction in the number of CNOT gates required per quantum circuit. So if we get up to systems with 50 hydrogen atoms, we might see CNOT gate reductions of 2 orders of magnitude. And this is just due to the difference in scaling of the circuit depth in either of these cases. So we also can apply our complexity theoretic analysis to the non-orthogonal quantum eigensolver, which is some previous work we did here, where we use unitary coupled cluster type reference states in different orbital bases. I'll sort of breeze through this slide, and here are some results from toy models. On the left panel here, this is a diatomic H2 molecule, and on the right it's a square planar H4 hydrogen atom arrangement. And with some appropriate scaling of parameters obtained by classical methods, we can get answers within chemical accuracy over this whole dissociation curve without requiring any hybrid variational optimization. And we're currently thinking about ways to combine the circuit depth reduction of TNQE with the shock count reduction of NOQE. And this is an active area that we are thinking about right now. But just to wrap up everything that I've been talking about, if you take one thing away from this talk in terms of where can we look for quantum advantage in quantum chemical systems, we should be looking for quantum speedups in chemical systems that are characterized by both types of electronic correlations, or maybe it's better to think of it as something in between static and dynamic correlations, where you have like a large number of reference states that contribute greatly to the wave function, and then a sort of fat tail to the distribution. So you have many higher lying states that you also need to take into account. There are plenty of examples of these in quantum chemistry, such as stretched bond regimes, transition states, and many others. But since I am running out of time, I'm just going to wrap up there, and thank you all for your attention, and I'll be happy to take any questions.
Thank you, Oskar, for a very nice talk.
Okay, I've got a question still. If there's 1 minute, that will be before we depart. I'd really love to ask a quick question.
Please, Samuel. Yeah. Thanks for joining us. I see that you are in the car, so it's
I couldn't miss it.
Okay.
and I'm happy to be here, really. So I worry less about the complexity of computing matrix elements than the sheer number of these matrix elements and the consequences of that. So you showed a slide with a classical computer generalized eigenvalue problem where we have a multi-reference state and we calculate matrix elements with a quantum computer. And my question is, well, there'll be sort of m choose 2 elements in such a matrix. What is the typical value for m?
That's a really great question. So it's definitely going to be system dependent, and I think in general it should also depend on the circuit depth of each reference state that you're using. So there is typically a kind of width depth trade-off with these kind of things. So we are really interested in the low depth regime, so squeezing the circuit depth to be as short as possible. And yeah, you might naturally expect that there will be some trade-off in the number of reference states that you need to characterize the system. Okay. I think this will definitely be the case. So this is an active area of research, and it's very difficult to say anything analytically here. It's sort of a case where I think you need to run a lot of numerical simulations and see what the scaling really looks like in practice. So currently we've only really tested out these methods on small toy problems, but we are looking right now at scaling that up to more interesting chemical systems. Okay. So evaluating these matrix elements is not really a problem, or because I can imagine that one matrix element per one circuit evaluation, or is it to get all matrix elements at once? No. So you would need to run separate circuits for each of these matrix elements. Yeah. Okay. Thank you. Thanks.
Okay. Any other questions to Oskar? Okay, I might have one. So let's say, like, assuming that we have those, let's say, this class of multi-reference states, in which all those phi i's are actually tensor products of magic states, maybe. Yeah. Assume we are in such a situation. So what do you have some let's say example of because for those magic states, really, let's say you do have sort of hardness, right? So is there some are there some physical systems, some molecules where this type of ansatz actually captures well the Yeah, like the ground state, okay, such that you can actually
Right. So
in this
yeah,
ground
I think any kind of argument that you make here will have to be informed by empirical considerations. So just seeing what are the features of actual chemical systems. And here we do have some reason to think that. So focusing again on this last slide here. So one thing that we show in our preprint is that you can prepare the fermionic magic states using two-body fermionic excitation gates with amplitudes, two-body amplitudes on the order of pi over 4. And so in the first region of this, so this is kind of a sketch of a molecular dissociation curve. You have energy on the y-axis and bond dimension or bond length on the x-axis. So in the near equilibrium region 1 of this sketch, typically the two-body cluster amplitudes that you require in a sort of UCC SD type wave function are small. And it's not clear that you would be able to prepare this sort of tensor product of magic states type wave function using only small amplitudes. But when we get into stretched bond regimes, typically the two-body cluster amplitudes become large on the order of 1, which is what we are looking for as an indication that there would be a lots of non-Gaussian magic in that state, right? So it's definitely an empirical argument, but it is known that over a wide sector of chemical space, in these stretched bond regimes where we have a lot of static correlation, in addition to dynamic correlation, which is always present, then it is reasonable to think that we could see this sort of hard regime appearing in practice.
Thanks. I think Zoltan has many thanks. I'm happy with the answer. Zoltan has a question, please.
Right. So what I didn't get exactly from this type of discussion is like when you're thinking about that you can get an exponential advantage using a quantum computer. I mean, I'm a little bit afraid that maybe you are mentioning some particular methods where you can get it. Let me be more specific on this. So, for example, suppose that you have a circuit, okay, with, let's say, a fermion sampling circuit, okay? I will never be able to sample from that. However, if you tell me that I should calculate the expectation value of a two-body operator after the circuit, that's actually classically not so hard. Definitely not. It's polynomial. So like for a variational type of algorithm, I'm not even sure exactly what you mean. I guess you are here meaning of other types of algorithms. And can you explain me a bit? For example, what is your algorithm? I didn't completely get this tensor network, quantum variational eigensolver. And then sometimes you are mentioning some subspace method. I guess you mean this Motta and Mezzacapo type of methods, or which methods where they sample and then they look at the smaller, they only look at the part of the Hilbert space from where they get samples from, or can you, this is what I didn't get also from the paper, actually.
Sure. So TNQE is a subspace method.
Okay, so what does a subspace method even mean?
Sure, yeah. So I guess what we mean by subspace methods is that we have some set of correlated wave functions which spans some subspace, right?
Okay, I see.
And then we use a quantum computer to compute the off-diagonal matrix elements. So it's like embedding the Hamiltonian within this smaller subspace of reference states.
And then you classically
Yes.
diagonalize.
Yeah.
I see. Right. And in your method, can I have a look at your method? So how do you choose this subspace or the vectors from this subspace?
Yeah. So that's what I was. I mean, the details are in this paper. Our previous preprint, which hopefully will also be out in print soon. So the idea is that we developed in this paper was to optimize each matrix product state, co-optimize the parameters of the matrix product state and the orbitals using a hybrid quantum classical optimization loop, which is based on the classical DMRG sweep algorithm, but extended through subspace diagonalization. So at each step, we would optimize a pair of site tensors on each matrix product state by decomposing the two site tensor into some set of I refer to them in that paper as one-hot tensors. It's just a sort of local basis for each matrix product state. And then computing a larger Hamiltonian and overlap matrix in that expanded space, and then diagonalizing that to obtain new tensor parameters. And then we sort of intersperse this with an orbital rotation step, where we transform the molecular orbitals locally on each matrix product state. So each matrix product state sort of learns its own orbital basis and its own set of tensor parameters at the same time. So we found this strategy to be pretty effective in practice. The major downside here is the higher measurement cost, because if you think about sort of expanding a large matrix like this at each optimization step, that is quite a lot of matrix elements that you have to compute. It's polynomially scaling, but with a large prefactor. So what we're looking at now is ways to reduce that measurement prefactor further, and maybe try and develop a sort of one-shot version of this type of method, where you would sort of set up the basis classically and just compute the off-diagonal matrix elements on a quantum computer. But
okay,
that's sort of something that we're actively looking at.
So then that was now quite clear for me, but then let me ask you a question. So the only thing you prove here now, from my perspective, is to get that subspace on a shot-by-shot basis or something like that. That could be hard. However, I don't see any proof of, actually, I don't see any proof of that to get the full subspaces that you are actually taking out, not by shot basis, but somehow that is hard, okay? That I don't see in the different methods. Secondly, I don't see whether you cannot use another method, which is not a subspace-based method, where this is not a hard thing. So I mean, the only thing I see here proven is that if you make such a subspace-based method, you have to sample, and that sampling is hard.
Right. So I mean, what we're specifically trying to show is that what we'd like to show is that computing these matrix elements up to an additive approximation is classically intractable.
Okay, that's good. Okay, so these matrix elements were, once again, what? Okay, phi I, phi j were something, let's say, that encompass, could be also those high magic product states and so on. And the g were it was simply just orbital rotation, was an orbital rotation.
Yeah.
Okay, and age I was what?
So that's just the Hamiltonian expressed in the basis of state I. If you have the Hamiltonian on this side of the orbital rotation operator, then you need to express it in the orbitals of this reference state to be able to evaluate the matrix element, right? It's like I guess if you think about having two reference states, one is like gi phi I, one is like gj phi j, and then putting them on either side of the Hamiltonian, then you can rotate the Hamiltonian into the basis of reference state I, and then just have it on one side of the combined orbital rotation operator.